Simone, it's a pleasure to have you here tonight. I welcome you to us and look forward to hearing your presentation. Thank you.
Yeah, thank you, John, for this very kind introduction. And welcome to all of you this evening. And welcome not only in this lecture hall, but as you might have found out, also welcome to all those who are on the live streaming at this moment. Dear colleagues from Monash community, faculty representatives, teachers, colleagues, friends, it's a great honor for me. And it was a great honor for me to receive the Dean's invitation to this Dean's lecture, to provide some insights into my academic interests and achievements. And I'm more than grateful and happy to be here during these days and weeks as a visiting scholar here at Monash and to cooperate with the members of the Inclusive Mathematics Education Research Groups. So, but before I begin my lecture, I would like to say thank you to two very special people. I would like to mention Dr. Anne Downton and Dr. Sharon Livy. It is mainly due to their engagement, power, encouragement, and most friendly cooperation that I'm standing here in front of you today. So thank you very much for doing all this and for applying for all these things, administrative issues, and so on and so on. Thanks to you. Well, getting back to the topic of my lecture today, I intend to introduce some German perspectives on inquiry-based, research-based learning in primary mathematics education, and then invite you to share about consequences for the education of prospective primary mathematics teachers during their university studies. And for the introduction and for first example, let me take you on a journey to Germany. This is not Leipzig, not yet. But as you might be able to tell from these pictures, I grew up in a very small village close to the famous Pied Pipers town of Hamelin, which is also a very beautiful city. And close to the farm where I grew up, there were nice little willows with all kinds of farm animals on them. So let's pretend to visit one of those German farms. And let's think of 31 animals on that farm. And if this presenter worked properly, then we could go to the next slide. It's working again? Okay, here we are. So when the farmer brings all cows into the shed, maybe to milk them, only 16 animals out of these 31 remain standing on the farm's willow. It should show on here, but it doesn't. Am I too quick? Maybe. I'll just keep on talking and you have to think of all these numbers. Whereas if only the pigs were gone to the shed for any reason, there would be 21 animals on the willow. And if only the goats were missing for any reason, there would be 25 animals remaining on the willow. So this is a very hard task for you now because you didn't see the numbers. So, well, the question that you might have expected already is how many cows, how many pigs, and how many goats would there be on the willow? So let's just wait for a second to give you some time to think about this question. Now it's coming? Okay, now it's working properly, that's fine. So this is the problem. 16 animals without the goat, with the cows, 21 animals without the pigs, 25 animals without the goats. So whenever I introduce this problem to my pre-service teachers, they would all agree that this is far too difficult for children in grade 1. And indeed, this seems to be quite a complex situation when we have a look at the mathematical background. Of course, you can try to grasp the situation with equations using variables. So if C stands for the number of cows, B stands for the number of pigs, G stands for the number of goats, then we might come up with 4 equations saying C plus P plus G equals 31, P plus G equals 16, G plus C equals 21, and C plus P equals 25. That looks difficult, doesn't it? Well, if you display these relations slightly different in a triangle like this one, you may note the sums of the equations we have to set up on the edges of that triangle. Say that each field inside the triangle includes the amount of animals of a special kind. And the amounts of each neighbor fields are summed up on the edge of those fields, like this, for example. So then the amount of pigs and goats sum up to 16 animals, goats and cows sum up to 21, we know that, and cows and pigs sum up to 25. It makes it, well, not really very much easier at first sight to solve this problem now, but something has changed. And this is a different array of all the information we have, and we can look at this even at a more general way. So if the three fields of a triangle with any number x, y, and z are used in the way that you write the sums on all the edges of the triangle, say that x and y and z are your starting numbers and a, b, c depend upon these numbers, then again we can note equations using variables this time, and we get a set of linear equations. So no worries, I will not take you through all of these equivalent transformations now and all the substitutions that you would have to go through. But if you do apply all these strategies, you can definitely find out how to get to x, y, and z. And, well, of course, this looks complicated. And as I said, my pre-service teachers always said, no, we can't do it. We can't do this in grade 1. Of course you can't. You can't do it this way. But you can do it in a different way, and you can explore all these relations in a different way. So what is this very special triangle all about? You could make it stand upside down, but that's not so exciting. You could also say, well, there's some nice geometry in it. So there are some properties which might introduce you to draw a mandala or so. But yet at this moment, we want to look at this triangle in the way that it should frame our thinking of arithmetic relationships among 6 numbers. So my research on this went back to the 1970s, when this idea was first introduced by McIntosh and Quedling, who called frames of this and the similar kinds arithmegons. In Germany, this idea was taken up by Gerd Walter and Erich Wittmann, for example, and nowadays those triangle arithmegons still play a very prominent role in the textbook Das Zahlenbuch. And this is a page from a grade 1 textbook telling you what you can do with this arithmegon. So you can put counters into it, and you can try to find out how part relationships can be displayed in this triangle arithmegon, and many, many more things that I would take you to. So, for example, you could say, well, we go for a very similar example, like the one that we had with the animals. Using this triangle frame, invite children to explore the part-whole relationships, maybe use different approaches like a trial and error, or maybe even thinking in more detail about the relationships that come up. So this is what you can do in grade 1, and it does work. So in grades 2 and 3, you could also think of exploring sets of arithmegons, and I give you a minute to have a look at this and also at the solutions. So when you go for that task, you may well, just calculate and be happy that you found all the solutions. And then you check and you're happy and you go home. But you could also have a look at the different triangles and see that, well, numbers of the previous one always somehow return in the next one of that family. And once you found out this pattern, then you can find the next one and see if you find the next one after that, and so on and so forth. So what happens is that this is not only a frame for doing any calculation, but you can explore it, and you can explore the structure, and you can explore in what ways, well, the different ones in this set somehow belong to each other and how they are, well, developed from one to the next. The teacher, of course, and my pre-service teachers too, they should know in detail which different types of those triangle arithmegons may occur. So this is all in German, but no worries, you will find out very easily that, well, for example, these possibilities might range from fill all, put a number into all of the fields, and maybe have a look at a set of arithmegons and compare and share your ideas about that comparison, or don't fill any number with the task that students should find a set of arithmegons maybe themselves. And in another situation, a teacher might decide to go for this example that we've just had in the beginning. You know 3 numbers in the outer parts, and then you have to find out the numbers inside, or go for any other variation. I think this is a very important aspect of the teacher's exploration of this potential that the arithmegons obviously have. And we're only, well, hitting a very small part of that. There's even more potential when you think of extending the idea to a hexagon. So instead of just taking notes of the sums on the side of each field or on each edge, you write the sums in extending triangles. And in variation to what we did before, you can now have a look at the sums of all 3 inner numbers. In this case, the sums up to 12. And additionally, you could sum up all 3 sums in the extending triangles from this hexagon. Well, if you have a look at this example, you see that 24 is 2 times as many as 12. And kids in my own grade 3 classroom would soon get to the idea that the sum on the hexagon is always twice as many as the number, or the sum of the numbers in the triangle. But then the big question is, does this always happen? And how can we know? First step, search for many examples. And this is what we did. So if you have a closer look at these examples, there is a little collection from our blackboard, and with some kids, even in grade 3, then feeling very comfortable with smaller numbers, which is okay for the beginning. And some kids, well, are obviously being tempted to use very high numbers. That was in grade 3, and as you can see here, well, they were so influenced by this idea that they lost 1 0. Anyways, but the idea was to find many examples for the beginning. But many examples don't count if you find 1 counterexample. So in terms of an indirect proof, that is. So there seemed to be 1 counterexample. We were worried, Kids came up, they were discussing this counterexample, but fortunately it turned out that this was due to a mistake. So somebody got wrong with the calculation. So we were relieved in a way, but, well, how could we be sure that our hypothesis was true? So we went for colored little cards and put the numbers on them. and tried to display how we get to the sums in the extending triangles of this hexagon, which means we went through the process of filling in all the fields. Say that you have a 6 plus 8 in this example, and then 3 plus 6 and another 3 plus 8 in these extending triangles. And what happens if you then try to generalize? You just turn these cards and you end up with a picture like that. Which means, well, it doesn't really matter what number was on the red card or on the yellow card. It doesn't matter anymore, but you can see that the sum of the sums is always twice as many as the sum of the 3 inner numbers of the triangle, and you're done. And this is a perfectly, well, it suits, it's a good proof. It's a good proof for children in grade 3, as I see. So let's switch to a totally different situation in a geometry lesson. The task, which is supposed to invite children to explore mathematics again, is to take 24 cubes and to construct a rectangular prism using all of these cubes. So construct, maybe one. Construct many. Can you construct all? How can you tell you have found all? And these are some samples from a grade 3. We just worked last week with Sharon and Anne. They tried. They just took the cubes, they tried. Some were happy to find one, and we had to encourage them to find another one. Some tried to put down notes. They were expecting a lot of different rectangular prisms to come up. As you can tell, that was the plan. You know, I have to find 8. So that was the beginning for some of them. And indeed, they did construct different ones, and I think it's always so, well, it's always so wonderful to see with how many different ideas they come up. So they did drafts of their constructions. They tried drawings. They attempted to draw in perspective even, and they also had a look at the number of layers, at the number of piles. So they had this multiplicative thinking about it as well, right in the beginning, which was not influenced by us, not on purpose at least. And yeah. So, and this also challenges the high-achieving children to think about the question, if they have found all the rectangular prisms, if they have found 6. And indeed, you can write down all the multiplications using 3 numbers for the 3 dimensions. And if you go for the divisors of 24, these are the only combinations you can have using these divisors. So, this was not only a very, very long, extremely long introduction, but we made it through the first part of the presentation already. With examples from the mathematics classroom introducing tasks and settings where children are challenged to question, to explore, to discover and reflect on their discoveries. And throughout the rest of my talk, I will continue and reflect on these examples from a German perspective. I do this on purpose because I think it's quite, well, precious for you maybe, or interesting for you to not only get to see some more of your Australian framework, but to see more about what German colleagues have been doing about these tasks for a long time. So having a look at the frameworks for the work in school first, and then we have a look at what consequences get together with this when we have a look at teacher education. So as we have seen, the concept of inquiry-based learning in primary children's mathematics education refers to the idea of actively exploring mathematical issues. And one of the German scholars who I'm considered to be the most influential in this topic is Heinrich Wieland Winter, who unfortunately passed away early this year. He influenced a lot of the German-speaking community, or a lot of the German didactics, I must say, in a lot of ways. But one special idea was his idea about basic mathematical activities and skills. He calls it mathematische Grundtätigkeiten. And it was in the early 1970s already that he compared doing mathematics on a higher education level to activities in the mathematics classroom. In doing so, he expressed this idea that, or he stressed that doing mathematics on a professional level is very much about exploring mathematical structures. It's not only about applying rules, but it's more, like Polya says, like an experimental approach to a mathematical structure. And in line with Hans Freudenthal, a colleague from the Netherlands, he claimed that mathematics education should focus on these mathematical activities to plant these skills in the children, even at a very, very young age. This includes then the reason, or the skill to reason, to argue, and to justify your findings, to express, to document what you have found, to vary problems, and to apply your solutions in a new context. So in short, he says, if curiosity or research-like activities are a significant element of doing mathematics, then this should have consequences for the learning of mathematics as well. So he brings these two ideas together. Heinrich Winter's work strongly influenced the work of Erich Wittmann and Gerd Müller, two colleagues who have retired by now. They used to work at the University of Dortmund for a very long time. And they developed their concept of productive exercises. That's how they called this kind of task that they introduced. Produktive Übungen, they say. And these productive exercises are supposed to provide opportunities to discover, describe, justify any finding in arithmetics or in geometric patterns. They can be understood, treated, and continued on different learning levels, as they are not only very complex, as we've seen with the triangle arithmegon, but also open-ended. You can do so much more with them than you see in the first moment. And therefore, they allow access on different levels and different possible discoveries, and should also be connected, or you could be or should be able to connect them to other ideas in terms of networking them. This does not sound new to you, I know, because it's an idea which has been spread internationally in so many different ways. And I think one common root or so that we have in this field is the theory by Jerome Bruner about the discovery learning. Learners should construct their knowledge when they explore new topics in a self-activating way. We expect learners to develop their strategies themselves, not telling them what to do, but exploring the field and trying to find out. So, well, nobody noticed that it just went away? It's all right, okay. So it's all about the child's curiosity that the teacher should rely on. You should try to support them when they are in those problem-solving situations, and not tell them what to do, but let them discover what they do. So backing on the work of Winter, Wittmann, Müller, nowadays there are Swiss and German colleagues who elaborated this idea of working with productive exercises using the term natural differentiation, natürliche Differenzierung. And these two books are more or less bestsellers that I recommend to my pre-service teachers, including lots and lots and lots of good examples that have been tried out in various classrooms and so on. And the idea is always the same. The idea is always that you have one task for all children. Framing the lesson with this one task, with a low-level entrance for all of the kids, and all of them are working, yet they work on different levels, which includes also challenges for high-achieving children. They might work with less or more intensity. They might use different strategies or get to different solutions. That's all possible. They might use smaller or higher numbers. There might occur differences in their ways how they document it, how they reason, and so on and so on. But the frame is always the same for all of them. And this brings us to this idea that we have a lot of differentiation in the classroom, yet we have a social learning situation. It's not that they all work on separate ideas. They all have this one common idea, this one common task, and they have an opportunity to exchange and to go through social learning. So to sum up, the key positions of all these colleagues are more or less that we only learn mathematics when we do mathematics and when we apply the processes mathematicians usually apply. This is founded in a constructivist view on learning, where children construct knowledge themselves, more or less. This implies also that children need some kind of learning arrangements which enable them to refer to the knowledge they've gained before and then to negotiate on their ideas, attempts, solution strategies, and so on. So in line with that, Hirt and Welty, for example, comment on this idea in the way that they say there's also a need for complementary information. So it's not all about, I can discover just everything by myself, because there might be conventions or more information that I just need. And the teacher, of course, is responsible for also balancing this explorative to informative learning. And also they point out that das eigene, your own thinking, the kid's own thinking, is not supposed to get lost, which means that we should honor and value every child's effort and achievement in trying, and in trying hard, and in trying to find out. This is a very special attitude, I think, that teachers need to, implement in themselves also, to teach in this way. So, based on this, and meeting all these expectations, what does it mean to become a professional? If you want to use all these ideas in your classroom as a teacher, it's good reading about it, and it's good, watching other colleagues' lessons maybe or so. But, what about us? I mean, us as lecturers in university or advisors in school, principals, whoever. Can we simply teach the prospective teachers to do all this? Are they apprentice, or should they rather be researchers themselves? And regarding activities in undergraduate classes in teacher education, we might ask ourselves which activities might enhance pre-service teachers' curiosity for children's minds, for their ways of learning, for their conceptions or maybe misconceptions they have. Is it possible, it's a question, it's not an answer, is it possible that we prepare pre-service teachers to somehow enjoy and to encourage children's research and discoveries when we manage to, let them enjoy all this by themselves? Well, what has have to happen with them to make them switch their minds and do this shift from teaching to learning and doing research? So, as you can see from this quote here, that is Johannes Kühnel, a very well-known scholar in Germany from pedagogy, this discussion is not new. And university studies, not only in teacher education, but also in other fields or so, have always been struggling with this gap between theory and practice. So this is where I would like to introduce another very, very famous person to you, Alexander von Humboldt. So we can trace this idea of connecting teaching and higher education and research at university back to the concepts introduced by Alexander von Humboldt, who was born in the 18th century. He was a German philosopher and scientist, and he traveled all over the world and also founded the University of Berlin in Germany. And his revolutionary core idea of that time was a holistic view on higher education in general, with the idea that any lecturer and also students should be engaged in doing research by themselves to closely connect learning, teaching, and research. Not to separate them in all the situations, but in terms of trying to bring things together. So very similar to this traditional position, scholars in all fields of higher education argue that undergraduate research may contribute to overcome the gap between study in university and, for example, teaching practice. Yet these studies should always be relevant for the people conducting the studies. For example, in the moment when they are conducted, or for purposes later on in your professional life. Taking a particular look at the education of pre-service or in-service teachers, a colleague from Oldenburg, Meyer, says there has to be a link between theoretical and practical issues, and if we manage to find this interlink, then this contributes to the quality improvement of teaching. So when teachers do research on their own activities in the classroom, they may deeply reflect and elaborate their teaching afterwards. This is very similar to what Bernstein and colleagues call the educator-scientist model, which means to connect education, teaching to a scientific view on what you're doing, or what is known as a scholarship of teaching and learning. So Ludwig Huber, who's mentioned here on this term of scholarship of teaching and learning, he describes elements of the research process in a framework for university that he calls forschendes Lernen, which means learning by doing research. And these activities, this process includes, for example, to notice problems in the classroom and to set questions for inquiry, to find hypotheses, to identify relevant positions of a theoretical framework, and so on, to search for knowledge in the field, to select appropriate methods, and so on. This is a very helpful model, as I think, and I will get back to the basic ideas when I talk about what we are doing about this in our faculty. What we also found most helpful for framing our own activities in linking research and teaching in pre-service teacher education is a model introduced by Jenkins and Healy. They call it the nature of undergraduate research and inquiry. This time it's not a German framework, I have to admit, so I do look into the international literature, as you can see. And at first they say that you can think of an horizontal axis, which reflects on how much the students' activities put an emphasis on content, research content or outcomes or so, or if they rather refer to research processes and problems you might overcome. So then on a second axis, this model reflects on how much students are integrated in ongoing research activities. Are they more like visitors, an audience, or apprentices or so? Or are they engaging actively in doing research as participants in a research process? So there are 4 fields in this grid that they fill with 4 strategies, they call it, and say those activities could be, for example, research-led, So if students are more like an audience and the emphasis is on research content, then this is all about learning about current research in the discipline, learning research outcomes, and so on and so on. But then on the other three fields, they have these three different ideas, namely developing research and inquiry skills and techniques, just a very little bit of having an idea how we could do this and this and that, getting to know more about, for example, how an interview works or so. Undertaking research and inquiry then is on a higher level, you could say, in this model, and could also be accompanied by engaging in research discussions. So these are the four fields. I will give some examples for this later on when I refer to our own work. This was just to give you the first overview of this model. So based on all this, we find quite a lot of examples in literature where there's a claim to focus on inquiry and research-based learning in the professional development of mathematics teachers as well. So let's have a very short look at that, of course, as well, too. Professional development also for prospective teachers in primary school is also fixed in the German standards, as you can see here. So they tell us, our scholars in university more or less, to have a look on that. So engage them, go for it, let them do research. This is what these standards in 2008 told us to do. And among all concrete suggestions that you might find on how to implement research-based learning, it is a fairly well-known idea to prepare, conduct, and analyze, for example, diagnostic one-on-one interviews. And again, there's also some international colleagues among those. So stemming back to the positions of Heinrich Winter in a way, if curiosity and research-related activities are a significant element of doing mathematics, then the learning of mathematics for children should allow them to discover and to do research. And then I say if students should learn mathematics in a way where inquiry, research, and discovery play a prominent role, then also those who teach them should be experienced in doing so. So how could they teach if they weren't? Getting back to this model and having a closer look at our current work at Leipzig University, we try to follow more or less these strategies. We try to set up some ideas to get our curriculum working better in this sense. So in year one, our prospective primary teachers, the pre-service teachers, they take workshops, for example, on arithmetics and geometry in primary. And in these workshops, we, of course, let them experience some of the material. They also get into contact with these arithmogons or so. They do all kinds of this. But in terms of research, we just teach them about some research results. Then in year two, they take workshops on measurement and modeling in primary. And this is the first time when we introduce, we of course discuss information and about research results, but we also have a closer look at research processes with the idea that, they should find out how those research results turned up, which means having them think about how could an interview look like if you want to find out about some children's idea about measuring length, for example. What questions would you ask if? And well, maybe you have a child in your neighborhood. You could do this and this and that, and just try and look for this and this and that. So you found something in literature, try to copy it in a way. So we do all kinds of these little, very, very little studies with them in these workshops. And then, when it comes to next year, in year 3, they take workshops on math in kindergarten, which means, well, kindergarten up to grade 2. We call it Anfangsunterricht, which is beginning of learning in school. And in these workshops, we really try to engage them into little research projects for the first time. So what we ask them to do, it's got something to do with a little project that we have. We were lucky to get some funding for a place we call Lernwerkstatt, Learning Laboratory in direct translation. That's a place in our faculty, some rooms in the faculty building where we have all kinds of hands-on materials. We have a little library, we have well, some technical support, some computers, some cameras, and so on and so on. And this is a place where we can invite children to come to our place, invite schools, invite classes, teachers to come to our place. And this is a place where we situated the project Mathwerk. And to say it very, very briefly, the first part of the semester goes that way that we develop arithmetic and geometrical tasks with natural differentiation for kids, well, 5 to 8 years or so. And then in the second part of the semesters, the kids turn up. And the pre-service teachers teach the guests. So the children come in and they have a look at all the material, and then the pre-service teachers take over, and it's not only that they conduct this lesson or this little experiment or so, but they are also asked to conduct interviews with single children or to observe what they're doing, and so on and so on. So we put the cameras out and we try to grasp all this, and then later on in class we discuss about all this. So this is the little project, and then they write their assignment about it, and so on and so on. It's the same kind of work that you are doing as well, of course. This then prepares for their master thesis, or what we call thesis for the first state exam, which is can be compared to master thesis. And in these studies, they really deeply engaged in research discussions in class or among peers. They conduct research under, let's say, observation or surveillance or whatever, and they contribute to our research. And this is not only quite efficient in some sense, but it also helps a lot to engage them into the research which finds an audience outside university, outside our university. So let me introduce just one single, very small geometry project which serves as a wonderful, well, just say research playground or so for pre-service teachers. In 2012, we started this project, Y-Cubes. It's all about block building, and it's very much interested in how children construct cube buildings, buildings made of rectangular prisms, and so on and so on. So the idea is that when having them construct a building, this is also a way for them to express anything about their spatial abilities, anything about their spatial structuring, and so on. So in the interviews that we have been conducting since 2012, the kids have to copy, they have to mentally structure a building, they sometimes need to mentally separate, assemble, sometimes rotate, and so on and so on. The foundation of that project refers to my own dissertation and to other colleagues' PhD studies, and also, well, in a way, as a close connection to this idea that drawings are always or very much appreciated to give an insight into the internal representation a child might have in terms of spatial abilities or structuring strategies. So very, very briefly, this model was one of the results from our studies, namely a model of activities or elements that we discovered when children constructed with blocks. I will not go deeply into that, but just to give you an idea of what we observed, this model in the end helped us to describe what the children did for their constructions. Very, very short. And then this framing invited pre-service teachers to conduct their own studies and to do many smaller studies inside this framing, for example, using this model and trying to apply it on their own little study. So they tried to maybe extend it in a sensible way, or they discussed, according to their own research outcomes, that we should put something differently, and so on and so on. So they, for example, observed children constructing with cubes for Fröbel's gift, or we had studies where they used only drawings, or they took photos where they had to copy the construction afterwards. Some of the kids also had to construct on a mirror surface, which meant we had the model and the children had to copy it, taking into account that the mirror, has also something underneath the surface, and if you make that count as well, then you have to go for another construction strategy, of course. So this also connects, enumeration to geometry then, in a way, and that was one of the studies in 2013, for example. And then we also had some pre-service teachers who tried this game, which we published in 2015, using these cards that you can see here on the left side. And the children have to copy this building, which is on the card. So, to sum up again, these were only very small examples, but to sum up, in all these settings, pre-service teachers act as researchers. They investigate children's conceptions, which also helps them to acquire knowledge for their own prospective teaching. This definitely contributes to pre-service teachers' professional development and also contributes to mathematics education research, as I just said. So, but then there's also another dimension, as I think. Because, the only group of people missing in that concept is us ourselves. It's the scholars teaching the pre-service teachers. And it's the question about how should our professional development look like? Should it also be in some way an inquiry-based, research-based learning? So, have you ever thought about investigating pre-service teachers' conceptions, their misconceptions, their strategies in doing something? Do you think this might help us to acquire knowledge for our own prospective teaching? When I go to staff rooms in university or to meetings, I come across a lot of, talking about, this assignment went well, and we have to go through that exam once more, and did you see that, did you see that? But do we ever have a closer look at our pre-service teachers? And might this also contribute to our own professional development? As a last point, in this, following this idea, I would like to introduce the project Diagnose Pro to you. In this project, we had a look at the pre-service teachers' strategies, and we tried to find out what diagnostic strategies they might use when they diagnose individual arithmetic approaches in one-on-one interviews with children at the beginning of grade 1. So what we did is, these are details about the research questions, I will skip that. What we did is, after trying a lot of different methods, we asked the pre-service teachers to watch a video clip of an interview that had been conducted before. Sometimes they had conducted it themselves. Sometimes it was a video that showed other pre-service teachers. And they were requested to stop or to comment on scenes then and to say what they just learned about some child's conception or mistake or whatever. In these interviews, on the interviews, the interviewer also asked them to explain why they would think the child had done well or what the problem was and so on, because we wanted them to come up with a lot of hypotheses and a lot of thinking about it. Analyzing all this data with grounded theory methodology, we developed a model that tries to grasp elements of the what we call diagnostic process. Again, we cannot go into detail at this moment, but you see that it's not only, well, I collect information, then I interpret, and then I conclude. It's got so many more facets that we see even in the pre-service teachers analyzing the data, that I think this is most interesting. And we have used this model for a while by now. I have a doctoral student who is backing up on that at the moment, with the idea that we could use this model also to have a look at the development, for example, during a workshop. Say we have a look at what they diagnose in the beginning of the workshop, then we do a lot of work, we work with children, we go to classes and so on and so on, and we could also then have another interview at the end of that workshop, let's say 3 months later or so, and then see if anything about the strategies might have changed. And this is what we're in right now. We're trying exactly this model and trying to implement it into the evaluation of our classes. So, to conclude, this lecture was meant to remind us that mathematics education in school should support inquiry and research-based learning, that we should challenge the kids, allow them their own discoveries, sharing of ideas, attempts, and results. Then my demand, and that of other colleagues as well, is that this should result in pre-service teachers doing research and be engaged in inquiry-based learning themselves. And then the third dimension, which we should all think about, I think, and which, well, even for myself, I'm not clear with that so far, but it is a task for us to think how we, which means university staff, advisors in university or in school, how we could think about ourselves and how we might elaborate in terms of inquiry and research the pre-service teachers' research on the kids' research. So this is a double-decker in that sense. So I hope you learned not only about German animals, which are different from kangaroos and wombats and whatever, but you got a glimpse of what inquiry, exploration, research, discovery might mean to children in primary, how this could and should influence our curriculum and teaching of pre-service teachers. And please keep in mind the Pied Piper of Hamelin. Say, how many rats did he take out of town? How many kids did he take out of town? Did he take as many kids as rats? Who knows? And if you think you knew, how can you tell you knew? So stay curious. Thank you.
So we have an opportunity, some good, very good timing, as you would expect of a mathematician. So time for a few questions. Daniel's got the microphone. I meant to say earlier, and Simone picked up on it, we are streaming, and there are 40-odd people out there in the ether, and I should have recognised that. So we need to use the microphone, not just for here, but also for streaming, for people to hear. So we'll take a few questions. Don't be shy. Here we go. Thanks. Microphone on the way.
Hi Simone, I'm Gil Kidman from Monash. I work in the area of science predominantly, but also have a maths background. And I'm wondering if you go right back to the beginning of your presentation, you're talking about working with the children in the triangles with pigs and cows or counters or whatever. Do you actually use any of your research in an interdisciplinary nature of combining, say, those mathematical principles with the real world so that the child can actually see maybe there is some merit in this maths, or it's just fun in triangles and hexagons?
It's a very good question. Thank you. Well, I'm always struggling with that because, because when I was a very young teacher, I was very fond of any kind of packaging things and making mathematics smooth for the kids and saying, well, if you introduce it in a way they might come across what they might meet in their everyday life or so, it makes it easier for them. But then I met Erich Wittmann, who introduced this idea of why don't you do pure mathematics with the kids? It's fun just having a look at the numbers and just having a look at the patterns. And, well, to be honest, I have some written work in my office, which I don't dare to take out for my pre-service teachers because it's all about packaging, you know, telling stories about what's not really mathematic about an issue. Say you have wizards or so doing wonderful things, but it's also wonderful to just have a look at numbers and to just have a look at shapes and how they match and how you could explore all these things. It's a fantastic world. But it's also, and I agree, it's also about being able to apply mathematics to your everyday life. And I think we need to find this balance, which is sometimes quite hard to find. But I will always find most joy in having the pure part of the mathematics, to be honest.
Hi, Simone. I'm Jill. I'm from Monash.
Well.
Can I ask you to talk a little bit more about something that was on one of your slides about the balance between inquiry and I forget the other word that you used.
Yeah.
In Australia, we talk about inquiry and explicit teaching is the phrase that teachers are using at the moment. But I think possibly in the Australian context, our teachers are more likely to teach mathematics in an explicit, in an explaining sort of way. So what I'd like you to tell a little bit about is how do we encourage a balance between inquiry and whatever the other one was that you said?
Difficult questions, Jill. I don't know how to solve Australian problems because we have so many German problems about that as well. Because what I'm talking about is not everyday life in school, of course. Of course, we have a lot of teachers in Germany who do it in a very, very traditional way and who would tell my pre-service teachers when they turn up for their practicum also, forget everything that you've learned in university. I want you to teach properly, you know? And especially in the state of Saxony, where I'm working at the moment, there's a very traditional look at what school should like, what teaching should look like. And the best idea is, well, to just try and never give up. I have no solution for that. It's something that I really struggle with at the moment as well, because as I said, I'm very influenced by Erich Wittmann and the work with his textbook, das Zahlenbuch, and I worked for a very long time in schools in the western part of Germany, in North Rhine-Westphalia and in Lower Saxony. And now that I came to a different part of Germany, I find, well, there's a different culture. There's a different culture about teaching in schools. They succeed, and they succeed, well, in a very impressive way sometimes. but it's not what I want my pre-service teachers to learn and to implement in school, of course. So what we do is we try to provide them with lots of examples and encourage them every time we talk about the ways of teaching. Well, what else could you do? Maybe anybody else has a good idea that I could take home to Germany. I'd love that, maybe later on.
Hi, Simone. I've got a comment from Pen, who's from Monash as well. She and a few other people have agreed as well that they've just really liked the reference to values in inquiry-based learning and respecting children's efforts and achievements. And she has a question to follow on with that. Do the children ever count the total of their hexagon, including the inside triangle?
Okay, say the last sentence again. The total of the...
So do the children ever count the total of the hexagon, including...
You mean the inner numbers as well? Yeah, they do, of course.
And including the triangle.
That happens, of course. That happens. And if you explore this framing again, it's just that you have to make sure what rules to apply when you use it. It's the same in any explorative situations. You could use it this way or that way. And if it happens, it's good that it happens. So any misunderstanding is wonderful because it helps us to clarify. And that's what mathematics is about. You know, whenever you have a misunderstanding, you can step back and have a look at it once more and then, you know, agree on the ways you want to do it next step.
Hi, Simone. I'm Ian, and I'm a secondary teacher. This question relates a little bit, I think, to your second response a moment ago. To what extent do you continue to have involvement with your pre-service teachers, if any, once they've begun to teach in a school? Are you able to maintain any ongoing, long-term work with them?
Well, I haven't done this in detail so far, but in Leipzig we have the perfect situation that Leipzig is situated right in the middle of a place where a lot of people return to, and they come to our learning laboratory, for example, to get some materials even years after they have graduated. So I stay in contact to at least some of them. In informal ways and sometimes also in more formal ways, because at the moment the state of Saxony gives us a lot of money, to say in short, to educate lots and lots and lots of prospective teachers, which means I have a lot of positions, job positions, for example, at the moment, where they can apply for, and then sometimes after 2 or 3 years, they turn up again and apply for those lecturers' jobs.
Yes.
They do, and then that's how I get into contact with some of them. But at the University of Leipzig, I've only been there for 3.5 years now. Okay. So it's not a very long time to see what happens after 10 years of teaching or after 15 years of teaching. But that's a good idea, definitely, to have a longitudinal, study maybe on what turns out after 10 years.
Thank you. To follow up, yeah. It is reasonable, I presume, to expect that we might have a longer term effect were we able to maintain this sort of work with teachers right through their careers. Mm-hmm. I guess that's a fairly obvious answer.
I think it just takes a very, very long time. So Wittmann and Müller, for example, working at the University of Dortmund, they have a very, very strong team, let's say, and once a year they invite approximately 500 to 600 teachers or so to a symposium. And this has such power to the whole region they work at, to the whole state of North Rhine-Westphalia, I must say, that I wish I had some kind of an influence in Saxony. But, it just takes time, you know. They've been doing this for such a long, long time. And as I said, in Saxony or in other places of Germany, this has to grow. And it will take some time to plant these ideas into teachers' hearts. Or how could I say that?
Thank you.
Time for one more? Yeah, back. Thank you.
Hi Simone, my name is Jade and I'm a first year education student at Monash. As a pre-service teacher, it's quite daunting just to teach straight maths, like just plain maths. And I was wondering, for many of us, we feel a bit of anxiety when it comes to mathematics. I know personally literacy is more my strong point. What tips would you give to pre-service teachers who might feel a bit anxious about teaching mathematics, especially when you have such differentiation within a classroom?
Again, I cannot just say one sentence and it's all solved. I think the first point is that you have to be very clear about the mathematics that's behind the task that you're introducing to the children. So as I said, well, those linear equations, they will not turn up in your classroom, but you yourself, you should be sure about the background, of course. So the best thing for being a good teacher, even in primary, is to do your mathematics well. That's one recommendation I would give. So, and then you don't have to be anxious about what might happen, because once you have anticipated all the problems and all the difficulties that might occur, then it will make you feel much safer in the classroom to go through, well, ups and downs and to discuss things and to see immediately that something might have gone wrong in some kids' understanding of the task or so. So this will keep you self-confident in what you're doing. And I think that is a very important point. And the self-confidence doesn't come, well, it's not falling down from somewhere. It's all relying on your mathematics education and your own professionalization, I think. I'm convinced about that.
So let me just say a couple of words about the presentation and thank Simone publicly for it. A couple of takeaways, and these last couple of questions are very interesting. You start to think about the learning that we've all usually experienced in school, and then you try to translate that into what it means to be a teacher educator. And one of the great challenges in teacher education is not to repeat the status quo of our own successful school experience. So if I think about what Simone's second last slide was, she's giving us a strong insight into the nature of what it might mean to learn to teach mathematics in particular, but in an inquiry method. It's paying attention to the curiosity, the creativity, the opportunity to engage with mathematics as mathematics. And to think about researching that to shape the nature of giving control of learning to the learner. And then at the third level, as a teacher educator, what does it mean to actually research that within our own practice to create the freedom that allows that type of learning to be experienced by pre-service teachers, to give the encouragement to do the same in school. I mean, they are powerful messages about teaching and learning, and why in our political age the notion of teaching as telling and testing as knowing is so difficult for us to reconcile against quality arguments about teaching and learning. So that's what I've taken from you, Simone. I think it's been a very powerful and interesting argument. It is based in maths education, but it clearly abstracts across all areas of teaching and learning. It genuinely is what developing a constructivist learning approach hinges on. So on behalf of everybody, Simone, thank you. Thank you for being here. Thank you for sharing ideas, and thank you for challenging.
Thank you so much for having me. Thank you. Thank you for your comments.
And thank you very much for coming. Another wonderful evening and another great themes lecture. Thank you.
Thank you.